Hello everyone. Today we're going to talk about section 1.1 functions and their graphs. And I want to start off the lesson by talking about a definition. So a function f from a set D to a set y is a rule that assigns a unique value f of x in y to each x in D. All that really says is that if you have a function, it's going to take a unique value from set D and map it to set Y. So the relationship there would be that you would have D, an item from set D, being thrown through the function, and then being mapped to a set Y. So one specific element from set D will be mapped to set Y, and that's kind of the rule for a function. So let's look at some things that might be functions and might not be functions. So let's look at this mapping here where we have -1 going to 1, 1 going to 1, 7 to 49, and 5 to 25. So you notice we have this, this would be our set D, and this would be our set Y. And the set D is all the possible input values, called the domain, also known as the independent variable or the inputs. So the set D are the input values, and you notice that each input value maps to a single output value. So each input value maps to a single output value. Now, it's okay for one output to be, or one input to go to an output and another input go to that exact same output. A good example of this would be like if somebody runs the football in for a touchdown versus somebody catching a pass for a touchdown. Either way, the outcome was a touchdown, so the output was a touchdown, but the two inputs were both mapping to the same output, which was the touchdown. So domain, and then we have this other set Y, which is called the range, which is also known as the dependent variable or the outputs. So because each domain, number in the domain maps to a single range output, then this is a function. Again, on the middle one, each domain value maps to a single range value. So this is, again, a function. And then we have something that's not a function. You have a single domain value mapping to two different outcomes. So you can't have that for something to be a function. You can't have one input mapped to two different outputs. That's like paying for two different items with the same dollar bill. All right, you can't do that. I mean, once you use that dollar bill, you can't then use it again. So, and have it still be a function. So this is an example of not a function. Let's go through and look at some domain and range values. So domain values are all the different possible inputs for our function, and the range values are all the possible outputs. So if we look at the y equals x squared function, every time we put an input value in for x, we have to square it. So we have to talk about the restrictions. Are there any restrictions for x squared? Well, not really. I mean, you can plug any number in and square it. Like any number in the real number system can be squared. So our domain is going to range from -infinity all the way to infinity, because we can plug anything in. However, for the range value, when you plug in a number and square it, you're always going to get a positive number. No matter what negative number you throw in, you throw in -4 and you square it, you get 16. So no matter what you plug in, the smallest possible number you're going to get is 0, because if you plug in 0 and square it, you get 0. So we're going to have the all positive numbers for a range value. And I have to put a bracket on the 0 to make sure that I include it in the set. So if I don't put a bracket here, then 0 would not be included. So I put a bracket so it is included. Now let's look at the function y equals 1 over x. So you could write this a little differently, like so. but we're looking at the denominator. The denominator plays an important role here. So we can plug anything in for x except for the number 0, because if we plug in 0, now we're dividing by 0, and we all know that you cannot divide by 0 because in this case 0 cannot go into 1 a certain number of times. It's undefined. If you say, okay, how many times can 0 go into 1, you can't come up with a number. So that's a undefined process, and so the only number that doesn't work there is 0. So we're going to go negative infinity up to 0, parentheses so we don't include it, and then we're going to union 0 to infinity, because any number can go in except for 0. And now when any number goes in and we plug those in, we are going to get numbers that are going to range from basically negative infinity, because if you plug in a negative like 0.00001, you're going to get a really large negative. And the same thing goes for the positive, 0.0001 for a positive number. If you plug it in here for x, because you're dividing by a small number, you get a really large number. So we can get really large negative numbers. We can get really large positive numbers. We can also get really small negatives and really large negatives. The only number we can't get is 0, because if you're taking 1 divided by something, you're never going to get 0. So we're going to have the exact same set of numbers for the range. And then we look at square roots. So you have to ask yourself, what's the only set of numbers that you cannot put into a square root? That set of numbers would be the negative numbers. So if I plug in a negative number and take the square root of it, I get an undefined in my calculator. So I know that the smallest possible number is 0 to infinity, that I can plug into that. And then that just goes to show that our range, if you plug in 0, the smallest number is going to be 0. Square root of 0 is 0. Anything above that is going to be a positive number. So we're going to go 0 to infinity for the range as well. And now we're going to look here at this square root. Now we have 4 minus x. So let's just start plugging numbers in. So if we take 5 and we put 5 in for x, we get 4 minus 5. 4 minus 5 is negative 1. We can't take the square root of a negative, so we can't use 5. If we put 6 in there, 4 minus 6 is negative 2. We can't use 6. So right now that's telling us that we cannot use any number that's 5, 6, 7. Can we use 4? So we plug in 4. 4 minus 4 is 0. Square root of 0, 0. So we can use 4, but we can't use 5. So that means that the 4 is going to work. That's going to be our highest number that we can use. Put a bracket on it. And then if we plug in, let's just say we plug in any negative number. Let's plug in negative 2. If we put in negative 2 for x, you subtract a negative. When you subtract a negative, that adds. So you end up with a positive number in here. So any negative is going to work, because the negative will become positive. So we're going to go from negative infinity all the way to 4. That's going to be our domain. Let's look at the range value then. If we plug numbers in here, the smallest number we're going to get is 0 again. I mean, we can't take the square root of something and get anything less than 0. So 0 is still the smallest, and infinity is the largest. And now we go down here for this problem, we have 1 minus x squared. So now we're squaring something. This is going to change the pattern of our range, because now we're squaring a number and then we're subtracting it. So this is going to be a little bit different here. Let's try let's try a 2 in here. If we take 2 squared, that's 4. 1 minus 4, negative 3. That can't work. So let's plug in negative 2. Negative 2 squared, that's 4. 1 minus 4 again, negative 3. So negative 2 and positive 2 don't work, which means we can't go either direction, negative or positive there. So let's try it ones. Negative 1 goes in there. Negative 1 squared is 1. 1 minus 1 is 0. So the square root of 0 works. So negative 1 is the smallest number that's going to work. And then obviously, if that's the smallest, if we plug a 1 in there, 1 squared is 1. 1 minus 1 is 0. 1 is going to be the largest. So we can go from negative 1 to 1 for input values for this function. 0 works as well because 0 squared. 1 minus 0 is 1. So if you notice when I was talking there, I was plugging the 1's in for the x squareds. Negative 1 squared was 1. 1 minus 1 was 0. So we know that at least one of our values can be a 0. But that's going to be the smallest value that we can get for a range. The largest value we can get, if you notice when I was talking there, if I plug a 0 in for x squared, 0 squared is 0. 1 minus 0 is 1. So square root of 1 is still 1. So our range goes from 0 to 1. So we can only get numbers between 0 and 1, which is kind of cool. All right, now we're just going to practice some graphing. I know a lot of you struggle with T-charts, and you use graphing calculators to basically come up with your graphs. It's an important skill to be able to use a T-chart. Input-output chart is also what it's called, to graph things. So what I'm going to do is I'm going to plug -2, -1, 0, 1, 2 in here. -2 goes in. -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. Then I'm going to go ahead and mark all these. -2, 0. -1, 1. And you can see 0, 2, then here, and we get a straight line that goes right here. So this is a linear function. I'm going to make a t-chart again for now this y equals x squared function. So we'll put the t-chart right here. Right here. xy. And I'm going to plug in a few numbers. So I'm going to do -2, -1, 0, 1, and 2. -2 goes in, you square it, that's 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So we're going to go 0, 0. And then we've got 1, 1 on this side, -1, 1 on this side. Then we've got 2, 4, and -2, 4. And so you get this parabola, opens upward. So y equals x squared. Standard quadratic function is mapped like this. T-chart, very easy to use. You can use it for graphing literally anything. xy. So now I'm going to go -2, -1, 0, 1, 2. -2 cubed is going to be -8. -1 cubed is going to be -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. So -2, -8 is down here. -1, 1 is here. 0, 0, 1, 1, and 2, 8. And you'll see you'll get a function that bends like so. We're going to talk about this later, but if you notice that this is symmetric about the y-axis, this is an even function. So even functions we'll talk about later, but they are symmetric about the y-axis. And odd functions are symmetric about the origin. Notice that it's the exact same here as it is here. It's just flipped and reflected over the origin. So we'll talk about that later. But using t-charts, an important skill to be able to have. Now we're going to talk about the vertical line test. So the vertical line test, it's a test used to determine if something's a function. Why does it work? Because when you draw a vertical line through the function, if it touches the function twice, that means it's got two outputs for the same input. An example here, we go through, vertical line test only touches the line once each time, so is this a function? Yes. And then we go right here. So for an input of -2, we end up with -4 as an output. You can see that right here. And then we also end up with 2 as an output. So we have the same domain value mapping to two different outputs. That is not a function. We talked about that earlier. Vertical line test This is a good way to test to see if something is a function or not. And again, you see that right here. They show you, right? One is mapping to a negative 7.32, and then the other one's mapping to a 1.732. So you cannot have one mapping to the same value, so that's not a function. So you guys can see how to use the vertical line test. I believe you've done that before. Makes things pretty slick and easy. Piecewise divine function. I assume that you guys are not as familiar with piecewise divine functions, so we're going to go through basically the process to graph these and find the domain and range. So let's look at x and negative x. So what this is saying is for x greater than or equal to 0, we want to use this function. For x less than 0, we're going to use this function. So that's why it's a piecewise function. It's just saying it's split up based on the values of your domain. So let's choose a t-chart here, and we're going to go with -2, -1, 0, 1, 2 again. If I plug -2 in, -2 is less than 0, so I got to use negative x, which when I throw -2 in with negative x, the negatives cancel, and I'm left with 2. -1 is less than 0, I plug it in there. Boom, it takes away the negative. I got a 1. 0 goes in. It's greater than or equal to 0, so I'm going to use this function now. So that's just 0. A 1 is bigger, so I just get 1, and 2 goes in, and I get 2. So I have -2, 2. I've got -1, 1. I've got 0, 0. And then, I'm going back up. 1, 1. 2, 2. What kind of function is this? This is an absolute value function. You can see that it's written right here. This was the absolute value function. And at the beginning, you see the absolute value symbol. This is the standard absolute value function. So let's do the same thing. Before I get too far, let's look at the domain. So what's the domain of the absolute value function? Well, I can plug anything in, right? It says x greater than or equal to 0, x less than 0. So the domain is -infinity to infinity. However, the range, the smallest possible y value is 0, and the largest possible y value is going to be infinity. I should put a bracket on this, because 0 is included in that. Now let's go ahead and look at the next absolute value function, or not absolute value function, the next piecewise divine function, sorry. And I'm going to use a t-chart here. And this says x less than 0, so I'll pick 2 numbers on that. We'll pick a number between 0 and 1, and we'll pick a number bigger than 1. So we're going to go -2, -1, 0, 1, 2. -2 goes in. It's less than 0. It says -x, so I'm going to get 2. -1 less than 0. I'm going to get a 1. 0 goes in. It says square it. 0 squared is 0. 1 goes in. 1 is between 0 and 1. Square it, I get 1. 2 goes in. 2 greater than 1. It says my output is just a 1. So what do you think? 3 if I put it in? Output of 1. If I put a 4 in, I get an output of 1. So at some point in time, every positive number is going to give me an output of 1. So I'm going to have a flat line there. So let's look at this. -2, 2. -1, 1. 0, 0. 1, 1. 2, 1. 3, 1. 4, 1. It almost looks like a chair here. If I drag this up, which is what would happen, I end up with almost a lazy boy. So it's a different looking graph. What's the domain? The domain is going to be all the real numbers. Doesn't matter what I plug in. The domain, no matter what I plug in, I have a function to plug that number into. Range, though, it looks to me like the 0 is the smallest number we're going to get, and we can get up to an infinity because it looks like this line will just continue to go up and cover all of the possible range values. So 0 to infinity. That's what we'll have there. And then let's look at this other piecewise defined function. So we have negative 2x minus 1 for x less than or equal to 2, and negative x plus 4 for x greater than 2. Let's go ahead and t-chart it. Now because I use 2 here instead of like zeros, I'm going to kind of focus on going above and below 2. So I'm going to say 4, 3, 2, 1, 0. And I'm just going to kind of plug these in because that splits 2. So 4 is greater than 2. So negative 4, or 4 goes in here for x, so I have negative 4 plus 4, which is 0. 3 goes in here because of x greater than 2. Negative 3 plus 4, 1. Now 2, it's less than or equal to 2, so it goes in here. It's negative, well, 2 times negative 2, which is negative 4, minus 1 is negative 5. You'll see there's a jump here. This is a different look at piecewise functions. So we plug it 1 in. 1 is less than or equal to 2. Negative 2 times 1 is negative 2. Minus 1 is negative 3. 0 goes in. Negative 2 times 0 is 0. Minus 1 is negative 1. So you'll look here. Let's see. 4, 0. 4, 0 is here. 3, 1 there. 2, negative 5. Right here. 1, negative 3. 1, negative 3. And 0, negative 1. So if I were to continue going, like with 5, 6 up here, I would end up getting a line that looks like this. So we end up with a line that goes this direction only, and then we get a line that's going up that direction. And there's our piecewise defined function. What's the domain here? Well, there's no restriction. It covers all of them. So the domain is going to be negative infinity to infinity. The range, let's see here. Are there any values that we can't get? It looks to me like there are no, we can get any value we want on that graph, because this expands this way, this expands this direction. If we pick some decimals, we'll cover in this area in here. So the range here is negative infinity to infinity. All right, so that was piecewise defined functions. It takes a little bit of time, but not overly difficult. Just got to kind of think your way through. Now we're going to go on to what we'll call the floor functions and the ceiling functions. So they call this the greatest integer function or the floor function. So I'm going to refer to it as floor. This is the key. In your homework, you have to pay attention to that. They're going to have a symbol that looks like this with the brackets coming down on the bottom. Well, that's on the floor, so that's why it's called the floor function. And what the floor function asks you to do is it asks you to find the greatest integer that's less than or equal to the number they have inside of here. So if we look at the examples, 2.4 is inside the floor function, and they want the greatest integer that's less than 2.4. So what's the biggest number that's less than 2.4? That's 2. And notice I said integer, so it can't be a decimal, it's got to be an integer. So 2.4, the greatest integer less than it, 2. 1.9, the greatest integer that's less than it is 1. 0, the greatest integer less than 0 is, well, that's 0. Negative 1.2, the greatest integer that's less than that is negative 2. 2, greatest integer less than that is 2. 0.2, the greatest integer that's less than that is 0. Negative 0.3, the greatest integer that's less than negative 0.3 is negative 1. And then negative 2, the greatest integer less than negative 2 is negative 2. They want us to evaluate the following. So we have the floor function for 2.7. Well, we know that that's going to equal, so if we have this floor function at 2.7, that equals 2, because the biggest integer that's less than 2.7 is 2. Part B, we have negative 1.4 inside the floor function. Well, the biggest number that is less than negative 1.4 is negative 2. And then finally, we have floor function for 8. Well, the floor function for 8 is 8. It's already the integer. and that's the floor function. You can see a graph of the floor function over here, and how they use that. Let's look at now the ceiling function. So there's a big long description of what the ceiling function is, but the ceiling function is the opposite of the floor function. So for the ceiling function, they don't have a bunch of examples of it, but we can kind of make some up. They want the least, so it says right here, the smallest integer greater than or equal to x. So before they wanted the largest integer that it was less than x. Well, now they want the smallest number that's greater than x. So they're going to represent it looking like this, and that's how you know it's the ceiling function, is because you have the brackets on top. So if we want to find the ceiling value of negative 3.2, we want the smallest integer greater than or equal to negative 3.2. Well, a number that's greater than or equal to negative 3.2 is negative 3. So that is the smallest integer that's greater than or equal to negative 3.2, because negative 3 is bigger than negative 3.2. If we look at 5.3, says the smallest integer greater than or equal to x. Well, the next integer greater than 5.3 is 6. So that's the smallest integer that's greater than 5.3. If we do like 7.1, that would be 8. If we did like negative 4.5, and we're looking at the ceiling function, that would be negative 4. So as you can see, these two functions are pretty easy to work with. You just need to know that the ceiling function is asking for a number that's larger, but that's the smallest integer that's larger. And for the floor function, you're looking for the greatest smaller integer. So I gave you plenty of examples. Use those examples in your homework. Now we're going to talk about increasing and decreasing functions. So for increasing and decreasing functions, it says let f be a function defined on an interval I, and let x1 and x2 be two distinct points in I. So basically increasing and decreasing functions are easy to figure out. You're looking from left to right on the graph. So if you move your pencil from left to right, you need to determine, is my function going up or is it going down? So if I put just a couple of functions here, you can see as I go from left to right, and I kind of botched that, that was a little bit off. This is like an x cubed function. But as you go from left to right, you can see that this thing is rising as the x value increases. So this is an increasing function. Whereas if you have it like this, as you go from left to right, this is a decreasing function. This is a decreasing function. If the function of x2 is greater than the function of f1, whenever x1 is less than x2, then f is said to be increasing on the x. All they're saying is, if your x1, let's just call this, and let's call this x2. So if x1 is less than x2, which it is, right? You can see if we're talking the x direction, from left to right, this one is smaller than this one. But the function for x2 is greater than the function for x1. Well, that's true because in the y value here, x2, when you take the function of x2, you're getting the y value. It's much higher up on the graph than this is. So that's why it's increasing, because x1 is smaller than x2, but the function of x2 is giving you a larger output value. So that's why it's increasing. And then this is just the opposite of that. It's saying, okay, if x2 is less than the function of x1, so if the function of x2 is less than the function of x1, whenever x1 is less than x2, so again, we pick x1, x2. You look here and you say, okay, well, my function of x2 is much lower on the graph, right? So it is less than the function of x1. Whenever x1 is less than x2, well, x1 is less than x2 because if we're looking horizontally, x1 is going to be a smaller horizontal number than x2, so that's why this function is decreasing. It's this is the more complicated version of just looking and saying, okay, from left to right, is my function moving up? Is the range of the function moving upwards, or is the range of the function moving downwards? So now they want us to determine if our functions are increasing or decreasing. So it says increasing over the interval x less than 1. So we want to find the function that's increasing over the interval x less than 1. So they want us to take these and put them in the right space. So let's take a look and let's see here. So increasing over the interval x less than 1. So x less than 1. So there's nothing here that's less than 1. So it can't be b. X less than 1. So increasing over the interval x less than 1. Well, if you notice, x less than 1 right here, that's where the vertex is. Well, if I go less than 1, this thing, if I'm moving left to right when x is less than 1, this thing is increasing. It says increasing over the interval x less than 1. That's A. And then I look at decreasing over the interval x less than -4. So let's go to x. Let's look for x less than -4. I don't see anything here where -4 is in. I mean, it's not the vertex of A. -4. I don't see anything here for -4. But right here, there's a vertex for -4. So it looks to me like this, it says decreasing over the interval x less than -4. Well, this is decreasing all the way up till x is -4. So this must be C. And then from -4 to 1, well, -4 to 1 is right here in that same one. It says that it's increasing. So that is C again. And then decreasing over the interval x greater than 1. Well, if we go back to this problem right here, let's see. From x is 1 right here, this is decreasing over it. So that's definitely decreasing right there for x greater than 1. So that's A. But then you also look here, and for anything greater than 1, this function is decreasing. So that would also be B as well. A and B are both decreasing over the interval x greater than 1. So these are just telling you for these specific input values. If you think about our piecewise divide functions, for this input value, we're trying to find the one that's increasing over it, decreasing, and so on and so forth. And so you just kind of look at the graphs and see, okay, where are these things increasing at? Where are their vertexes at? And where is it changing from increasing to decreasing, etc. And then if we look down here, there's some problems like these in your homework for sure. It wants us to give the interval for which the function is increasing or decreasing. So let's take a look at this interval here for this function. So we want to know when it's increasing. So for number 5, it's increasing from -4 and on. So, or sorry, not -4, -2. If you look at the x value, -2. So from -2 on, it's increasing. So we're going to say x greater than -2, it's increasing. And it's decreasing for x. If we say x greater than -2, it's increasing. We're going to say x is less than -2, it's decreasing. So it decreases for any number that's less than -2, but once it gets to -2, which is the vertex, it's going to turn back and increase. And then we look here and we look at the vertexes here. So one vertex is -4, so it's increasing for x less than -4. It's decreasing from -4 to roughly 1. So we're going to say from -4, we're going to box it in. So less than x less than 1, that's when it's decreasing. And then it's going to increase again from 1 to 5. So we're going to say 1 less than x less than 5. And then for this last little part here down there, we're going to say it's decreasing for anything after 5. So for x greater than 5, it's decreasing. That's how you do increasing and decreasing functions. So last but not least are even and odd functions. So I told you earlier on in the video that we would talk about even and odd functions. So they have specific characteristics. The graph of an even function is symmetric about the y-axis. So any even function is going to be symmetric about the y-axis, which means it's going to reflect across the y-axis. The graph of an odd function is symmetric about the origin, which means it's going to reflect about the origin. So when you reflect about the y-axis, it's going to be mirrored across the y-axis, whereas if you have an odd one, it's going to be mirrored across the origin. So when it's across the origin, it's not only flipped, but it's also upside down. When it's across the y-axis, it's just flipped to the other side. The easy way to tell if something is even and odd, if you plug in negative x into the function, and you end up with f of x again, the same function you had, you've got an even function. So if you plug in negative x into the function, you still end up with the same function, that's an even function. But if you plug in negative x into the function and you end up with a negative f of x, you've got an odd function. So let's take a look at what that looks like. So if I check to see if this is an even or odd function, all I've got to do is say, instead of f of x, I'm going to say f of negative x, and I'm going to plug in negative x in for this x here, which gives me negative x squared. Well, I know that negative x squared is just going to be x squared. So I ended up with the exact same function after plugging in negative x. That means that this is an even function based on this definition here. Now if I check this one here, again I'm going to say f of negative x equals, that'll give me negative x, and I'm going to square it, plus 1. When I square the negative x, that gives me x squared plus 1. I ended up with the same function that I had before, even if I plugged in negative x. That is an even function based on the definition. Now let's check this one. I got a feeling this is going to be odd. I plug in negative x in for x and I get negative x there. Well, if you notice right here, it says if I plug in negative x and I end up with the negative function, well, my original function was x, now I got the negative version of that. That is an odd function. So these two here are going to be symmetric about the y-axis. This one here is going to be symmetric about the origin. And if you graphed those, you would be able to tell their symmetry, because when you graph the function of x, you're going to get a line that looks like this, which you can see is reflected about the origin. When you do the x squared one, if you remember what x squared looks like, it was reflected about the y-axis. So you just flipped it to the other side and you had a reflection about the y-axis. So let's look at this one here. F of negative x equals negative x cubed. When you cube negative x, you end up with f of negative x cubed. So if you notice, we start with x cubed, we end up with negative x cubed. So that is an odd function based on our definition there. So this is again an odd function. And finally, we plug in f of negative x for this one. You're probably thinking that we never get a function that's neither. We'll take a look what happened. I plugged negative x in for x. I get negative x plus 1. That's not the negative version of x plus 1. The negative version of x plus 1 would be negative x minus 1. So I didn't get the negative version, but I didn't get the positive version, which means it's neither an odd or an even. So this is neither. And that's how you check to see if something's even and odd. That should help you out for your homework later on. And then the proportionality. So it says two variables, y and x, are proportional if one is always a constant multiple of the other. That is, if y equals kx for some non-zero constant k. So it says in this problem, let's just do an example. The variable s is proportional to t, and s equals 15 when t equals 75. Determine t when s equals 60. Okay, so we want to know what t is when s changes to 60. The original ratio was 15, s is 15 to t is 75. So we're going to use this equation here to figure out what our constant value, our ratio is. So let's take 15 and 75, and we got to plug those in for y and x. So you're fine. So we're going to put in 15 here. We're going to get k times 75 here. And we're going to divide that across, and that'll give us k equals 15 over 75. So then I'm going to put this into this equation again. So I'm going to take this and I'm going to put it into an equation at y equals kx again. Now I know k is 15 over 75, and I'm going to use s is 60 and plug it in for y because I plugged 15 in for this s in for y. I'm going to plug this in for y. So I have 60 equals 15 over 75 x. I'm going to divide that across. So when I divide 15 over 75, I'm going to get x equals 300. So they say it was proportional. So s, when s was 15, t is 75. Well, when s is 60, it's gone up. It's proportional. T goes up. Now t, or x in this case, is also could be represented as t, is 300. I'm going to show that in just one other different way real quick. But I could have just said 15 over 75 because it's proportional equals my s value, which 15 right there, so I'm going to put 60 over t, cross multiply, you get 15t equals 4,500, divide by 15, and t is 300. Now, I didn't show this way because when we do inversely proportional on this next example, so if you kind of look down at this next example, we have b equals k over a. We're going to need to use this to figure out this next problem. So let's go through this next one. So inversely proportional. Proportional means that the ratio stays the same. So we have s to t and s to t. It stays the same. Well, inversely proportional means one variable increases and the other decreases. So in the previous one, when one variable increases, the other one increases. That's proportional. But in inversely proportional, one variable increases and the other decreases. So they give us this equation, which is b equals k over a. And then they tell us the wavelength w of a wave varies inversely as its frequency f. A wave with a frequency of 800 kilohertz has a length of 28 meters. So right away I can plug in, let's plug in this 800 for b, and let's plug in this 28 for a. So we're going to say a is the, let's see, we said b is 800 and a was 28. I'm writing this down for a reason so that when I go to find this out, this 200, I know when I go to do the next part of this problem that this is going to be 200. Okay. So we go ahead and multiply that out. So we take 28 to the other side, multiply it. We get k equals 800 times 28 is 22,400. So now we know that if we use this equation again with 200 in for b, we know that k, which is the top letter in the equation, is going to be 22,400, and we're looking for a. So we're going to multiply crossed, and that'll give us 200a equals 22,400, and then we're going to divide by 200, and that means a is going to equal 112. So if we take a look at the problem, so the wave frequency of 800, you had a 28 meter length. Well, when that frequency dropped to 200, because they're inversely proportional, if the frequency drops, the length has to go up. The length did go up. So you can see that they are inversely proportional. And I know this was kind of a long video, but that is section 1.1. So when you guys come in tomorrow, we'll go over the homework, and you guys can do the homework problems. Get some help. Thanks for watching.